Hi, pre-calculus students. This is Mr. Buxton, and Mr. Isaacs and myself are going to do this video for what we were going to cover in class today. So we both appreciate the conversations that we had today about racial inequity and social justice, and this is the math material that we were going to cover. So there's 4 topics. I'll do the first 2, speeding up versus slowing down, and product rule, and Mr. Isaacs will do the second 2, the quotient rule and derivative of other trig functions. So for speeding up or slowing down, consider for a second a number line of velocities. So this is the numbers on this will be velocities. So 2, 4, 6, 8, 10. So here's 12, and 2, 4. Here's negative 12. So let's say we start at a velocity of 4. So v is equal to 4. And we go to a velocity of 10. V is equal to 10. So if my velocity is 4 and it goes to 10, then we're going to be speeding up. And that should make sense to you. So as the velocity increases, we're speeding up. Likewise, if we started at a velocity of let's say 6 and went to a velocity of 2. So here velocity equals 6 and the velocity equals 2. So my velocities are decreasing and I'm slowing down. So far this should make sense that when the velocity increases I'm speeding up, when the velocity decreases I'm slowing down. But we run into a problem on the other side of the number line. So on the other side of the number line, if my velocities are increasing, so let's say we go from a velocity of negative 8 and we go to a velocity of negative 2. So here, my velocities are increasing because I'm moving to the right. Negative 2 is more than negative 8. But because velocity is a directed distance, when my velocity is negative 8, I'm moving backwards faster than when my velocity is negative 2. So this would be slowing down. Basically, my velocities are getting closer to 0. So in that red arrow, my velocities are increasing, but I'm speeding up. But in the black arrow, my velocities are increasing, but I'm slowing down. So what we have to pay attention to is not just are the velocities increasing or decreasing, but we also have to pay attention to are the velocities positive or negative. So there's going to be 2 cases where we are, let's do one more where, let's say we're a velocity of negative 4, and then we'll go to a velocity of negative 12. So there my velocities are decreasing, because as I go from negative 4 to negative 12, I'm going to lower numbers, but I am speeding up because at negative 12, my velocity is faster than it was at negative 4. So this is speeding up. So there are 2 different cases where I'm going to be speeding up. And those cases are going to be here and here, right? So the 2 cases where I'm speeding up are going to be are the more obvious one. The velocity is positive and increasing. And then the other one is when the velocity is negative and decreasing. Basically, when my velocities are going away from 0. And the change in velocity is the acceleration, right? So another way of saying that the velocity is increasing is saying that the acceleration is positive. And another way of saying that the velocity is decreasing is saying the acceleration is negative. So for both of these, I can either have a highlighter. I can either have a positive velocity and a positive acceleration, or a negative velocity and a negative acceleration. So you want the signs of them to be the same for speeding up. And then slowing down are going to be the two cases where you have opposite signs for them. So you could be slowing down when your velocities are positive and your acceleration is negative, or when your velocities are negative and your acceleration is positive. So for these problems, what you want to do is you want to find the first derivative of position will be velocity, and then you want to find whether your velocity is positive or negative at that place. And then the second derivative, so after you take the derivative twice, will be your acceleration, and you want to find your whether your acceleration is positive or negative at a certain time you're looking at. The hang up for students is something says, is it speeding up or slowing down? Oftentimes students will just look at acceleration and be like, oh, the acceleration is positive, so I must be speeding up. Well, that works if your velocities are positive, but it does not work if your velocities are negative. So you have to look at both your velocity and your acceleration. And product rule. So for context for product rule, so far when we've been taking derivatives of sums, like if you had y is equal to 3x squared plus, let's say, e to the x, you would know that you could just take the derivative of each part and add them together. So the derivative would have been 6x plus e to the x. So this is basically saying that the derivative of a sum, let's do, is equal to the sum of the derivatives. So you find the derivative of f, you find the derivative of g, and you add those two derivatives together. It turns out that products don't work this way. So that if you wanted to find, let's say you had some function that was a product like x squared times the sine of x, that the derivative is not equal to just the derivative of the first part times the derivative of the second part. So there is a rule to find the derivative of products. It's called the product rule. And next year you'll learn the derivation of it, but this year we're just going to give it to you. By the way, you could sort of quickly confirm that you can't just take the product of the derivatives with a function like we could write y equals x times x. And so then you'd say, oh, well, the derivative of x is 1 and the derivative of x is 1, but we know that the derivative of x squared is not equal to 1 times 1, right? The derivative of x squared is equal to 2x. So we can't just take the derivative of each of the factors and multiply them. All right, so what is the product rule? So the product rule says that if you have a function y is equal to u times v, a lot of textbooks end up using u and v. You see them several times in calculus. I think it's a little bit annoying because u's and v's look the same and they keep using them, but as a convention it's often the notation, so we'll use it here too. The derivative of this product is the first factor times the derivative of the second plus the derivative of the first factor times the second. And so this is the rule that you can use whenever you're finding the derivative of a product. Let's say you're given that function we did on the last page, which was squared times sine of x. So y is equal to x squared times sine of x. Why don't you see if you can use that product rule to find the derivative. So pause the video right here and then unpause it and I'll do the problem out. All right, so hopefully you've done the problem out now, and maybe you found that the derivative was first part times the derivative of the second part plus the derivative of the first part times the second part. And it turns out with the product rule, it doesn't matter if you reverse any of those because both multiplication and addition are commutative, can be done in any order. So you could switch around which part you had, but in the quotient rule, it is going to be important to remember which part comes first. And then let's do one more example. So let's combine a little bit of stuff here. Let's say you had y is equal to e to the 5x times the cosine of x squared. I'll do the same thing here. Pause, see if you can do this derivative, and then unpause it and check. All right, hopefully you have gotten a chance to try out this problem. So if I'm going to take the derivative here, I'm going to take the derivative of the regular first part, which is going to be e to the 5x, times the derivative of the second part, which is going to be negative sine of x squared times 2x, because we have to remember the chain rule there, plus the derivative of the first part, which is going to be e to the 5x times 5, times the regular second part, which is going to be cosine of x squared. And you're going to find, if you're checking your answers in the back of the book for the odd problems, that they're going to do some simplifying of the derivatives once they find them in terms of factoring out. Like in this case, we could factor out an e to the 5x if you wanted, but you can also leave those just unsimplified if you want. If you are going to end up taking a second derivative, sometimes simplifying the first derivative helps a lot. Okay, and now Mr. Isaacs is going to show the rules for the quotient rule and taking derivatives of other trig functions and some examples that go along with them.
Hi everybody. As Mr. Buxton said, I'm going to go through the quotient rule and an example, and then also do some more examples with the other trig derivatives. You can follow along with this video on page 18 and page 19 of the ebook. So first we're going to talk about the quotient rule. Like Mr. Buxton said, using the variables u and v are really often used in calculus, and again, I'm not going to use them either because my handwriting is not that great and they're basically the same letter. So we're going to work with a function f of x. I'm going to use the letter t to represent the top and the letter b to represent the bottom function. So if a function can be written as t over b, then its derivative, f prime of x, is going to be the bottom function times the derivative of the top minus the top function times the derivative of the bottom, all over the bottom function squared. So if we look at this example here, our directions are to find a prime of x given the function 20 over sine squared of x. Pause this video here to come up with a solution to this problem. Great. Now that we have the solution, let's go over it. So a prime of x is going to be, so the bottom function is sine squared of x times the derivative of a constant, so that's going to be 0, minus 20 times the derivative of sine squared of x, which is going to be 2 sine x cosine x, all over sine to the 4th of x. So when we simplify this, a prime of x is negative 40 sine x cosine x over sine to the 4th of x. Some of you might recognize in this second to last step the 2 sine x cosine x as one of our trig identities for our double angle. You could rewrite this function as 20 or negative 20 times the sine of 2x over sine to the fourth of x. I recommend going this way because, as Mr. Buxton said before, if you're taking a second derivative, we want to try to keep things simple. So you can leave it like this, but completely simplified, we would have 40 cosine x over sine cubed x as our final answer. So let's move on, page 19 in our ebook. Now that we have the quotient rule and we know some other ways to rewrite tangent, secant, cosecant, and the cotangent functions, we can use this information to now come up with their derivatives. So we know that tangent can be rewritten as sine of x over cosine of x. Pause the video here and come up with the derivative for your tangent function. Great. So we should have gotten sine squared of x plus cosine squared of x all over cosine squared of x. And I see another Pythagorean identity, so we can simplify. And if you look in any calculus textbook, we're going to simplify this all the way down to secant squared of x. Let's rewrite our secant x function as 1 over cosine x, the cosecant function as 1 over sine of x, and our cotangent function as cosine x over sine of x. Go ahead, let's pause the video again here and find the derivatives of all three of these functions. Okay, great. So let's take a look at secant x, or the derivative of secant x. We should have come up with 0 or minus negative sine of x over cosine squared of x. And we're actually going to simplify this down like this to sine of x over cosine of x times 1 over cosine x. So our final answer here, the derivative of secant x is tangent x times secant x. Here we should have gotten negative cosine of x over sine squared of x. And we're going to follow a similar method here and rewrite this as negative cosine x over sine x times 1 over sine x. And we have negative cotangent x times cosecant x. Lastly, we're going to get negative sine squared of x minus cosine squared of x over sine squared of x. And if I factor out my negative here, my numerator, once again, is a Pythagorean identity. So I can simplify this to negative 1 over sine squared of x, negative cosecant squared of x. One quick thing to mention here, I'm just going to add in my derivative of sine and cosine here. Notice that these three trig functions have derivatives that are negatives. So cosecant of x has a derivative that is negative, cotangent x has a derivative that is negative, and cosine of x has a derivative that is negative. Notice that all three of those functions were our co-functions. Cosecant cotangent, and cosine. This is a little helpful hint that I use all the time to remember which trig functions are positive when we take the derivative and which trig functions are negative when we take its derivative. So here's an example that we're going to complete that uses both the quotient rule and incorporates some of these trig derivatives. So let's find the derivative of this function here, y equals 5 times the ln of 7x over cotangent of 14x. Pause the video here and see what you come up with. All right, so when we use our quotient rule, just to start, I know it's my bottom function times the derivative of my top function minus my top function times the derivative of my bottom function all over my bottom function squared. So this is a great start. It is not yet completely simplified, so we're going to go through a couple of simplifying steps here. So first step is 5 cotangent 14x over x plus 70 ln 7x times cosecant squared of 14x all over cotangent squared of 14x. So at this point, we've completely simplified everything that's in our numerator. Nothing really to simplify in our denominator, but I still have a fraction inside of my whole fraction here. So we want to take one more step and get rid of that. So the best way to do that is to split my whole numerator into two parts. So I'm going to take that first term over cosine squared of 14x, and then that second term over cotangent squared of 14x. So when I do that, I have 5 cotangent 14x over x cotangent squared 14x plus 70 ln 70x times cosecant squared of 14x all over cotangent squared of 14x. So I've got one more easy step to simplify in my first term. Those cancel out, so my first term here is 5 over x cotangent 14x. The simplifying in my second term is a little bit trickier. It's hidden here. Notice that I have cosecant squared of 14x, and in my denominator I have cotangent squared of that same value. So we could actually simplify cosecant squared of an angle measure over cotangent squared of that same angle measure, like so. 70 ln 7x over cosine squared of 14x. There it is. Great work, everybody.